So today I'm going to try and do two things. I'm going to try and repair this STEC flow meter, and I'm also going to try and make a video under 10 minutes. So I repaired a load of flow meters in a previous video, and this is one I'm going to use to figure out if they're actually still in spec. Now what's really nice about looking at calibration equipment is they have to use some kind of fundamental operating principle behind them that allows you to kind of precisely measure something, and that's super exciting as a scientist to be able to investigate that and see how they solved, the problem of measuring something from first principles, measuring something directly. Now these units have two parts to them. There's this top part, which is the actual flow cell itself, and they have the bottom part, and the top part's replaceable because you can get different scales of flow here. This top part here is actually where all the fluid mechanics happens, and we're going to pop this open and have a look at how it operates. And the bottom part down here, it just actually does the measurement. So I think probably the ADCs and other things are inside here, whereas the actual kind of measuring devices are all inside this one. What's wrong with it? Well, it won't power up, and I know pretty much why it won't power up. I bought this on eBay very cheaply, unbelievably cheaply, and I plugged it in, and immediately I could smell magic smoke escaping from the bottom. And then I had a look, and sure enough, I'm pretty convinced that the power supply had the wrong polarity on it. So I think whoever had sold me this bundled just any PSU they could find that was rated at 6 volts, didn't realize the polarity was the wrong way around, and I broke it, but using their wrong charger. So I've already taken apart some of the screws on this, and I've only left a couple in. Just to show you roughly how you take it apart, you can just take apart these 3 screws here and these 3 screws here, and then you end up with this. Now, what's really cool about this is it's kind of a combination of fluid mechanics and electronics and mechanical. There's a stepper motor at the back as well. So what happens is you pass gas in through here, through this inlet, it flows into this chamber here, then it flows up through this pipe, over the top, round this U-bend, and then back down again and out the system. It doesn't go back into the chamber. And how this system works is inside here, which you probably can't see. Yeah, you can just about see it. There's a metal ring, and there's also a spike. Now that spike is at the bottom of an inlet of that glass pipe, and that metal ring is meant to dip down into a filming liquid, a soap solution. In fact, for these types of meters, what you're meant to use is this Swagelok Snoop liquid leak detector, right? So this is something that bubbles like mad, but it's also non-toxic, non-corrosive, and so on. Anyway, you fill this bottom chamber here with Snoop, and then this small metal loop will dip down, create a bubble inside of it, then pull it over that spike. That spike is shaped so that it doesn't burst that film while the bubble's being dropped over it. And then you'll actually form a gas-tight seal because of that film bubble across the opening of this upper glass pipe. Then the film will move up, and then this detector will measure the time at which it crosses this location, and then you move it up to here, and you get a second detection of when the film passes back here. And what's really nice is that gives you a defined volume, right? The distance between these two detectors is known. The glass volume can be calibrated for, right? So basically how fast or how quickly this film moves from here to up here is how quickly it takes a volume of this much gas to pass through the system. So from first principles, this is really nice. You directly measure a volume of gas displaced. Now the problem is a volume of a gas isn't the same as a mass of gas, right? You need temperature and pressure to correct for the density of the gas. So they obviously need that in here as well, right? We want to get to mass flow, which is quite for our mass flow controllers. But here we have a very precise measurement of volume. Now, fortunately for us, the relationship between volume and pressure and mass and temperature is quite simple. It's just the ideal gas law, PV equals nRT. So as long as I know the temperature, that's only true for atmospheric conditions, low pressure, moderate temperatures. But that's definitely what's true here for the gases I'm going to look at in here. So, right, we need pressure measurements and we need temperature measurements. And here what we have is, I think, a temperature transducer. So they've actually bonded that directly onto the tube to try and get the temperature measurement exactly right here. The only other thing that I need, if I want to be really precise, is measure atmospheric pressure. And I'm assuming that's actually happening in the other box. Okay, I'm never going to make a video under 10 minutes, but let's see how we go. At the back of this, there's just a circuit board, and there's a little mechanical actuator, essentially just to move this ring up and down. I haven't actually taken the back off. We'll have a look at the back if we need to later. if we think that's where the problem is. There's a little bit of interesting design features here. So there's a little cap here that can pop off. The idea behind this cap is that you actually screw up some paper and throw it in there, and then its job is just to soak up the film as it comes to the top of this, so that you don't get the filming solution passing through the rest of your system. So you're meant to shove a little bit of paper in to just kind of break and absorb the films that come out the top. Okay, let's have a look at what the actual electrical problem is. Now, to take this thing apart, I've had a quick look at it already. All you have to do is to undo these 4 screws here, that are around there. I've got just 2 left, so I'll just quickly do them. Right, inside here, what we can see is a couple of boards. We've got a front panel board here. We can see some switches, some resistor networks up there, and a little processor here. But I think that's just probably a display driver, not actually much logic. And then we've got this board here, and what we could see is that they've loaded this board so that once the unit's assembled, any kind of calibration or anything else that you want to do can be done from this side. So oddly enough, we have this dip package down here on the wrong side of the board, but that's because this looks like a UV erasable EEPROM, so you program this with the software for the unit. And this little paper sticker here is probably covering a UV window to allow you to erase this EEPROM. I've got some clear test points here, so that'll be part of the calibration. Up here, I couldn't figure out what this was at first, but after I did a little bit of debugging on this board, I believe this is actually a battery connector. So this whole unit has the ability to charge a battery. So I think that's what this third state on this power switch is for. And that's probably part of where the issue lies as well, is in this battery charging circuit, because, you know, when we reverse bias this power in, that's probably damaged that first initial power circuit. Now, to remove this, you just have to remove these 4 screws in the corner. I've left one in from when I just pulled this apart at first. And there's 3 cables connecting it. So there's one I can access just at the top here. And once I've got that one over, I can flip the board open a bit more, and you can see there's a serial connection down here. And there's this display connector at the top here. Okay, so you see there's not much interesting inside this case, really. There's a Centronics connector, a whole kind of Centronics or GPIB connector at the top here. And that's just directly wired onto the board through the smaller connector. There's this 40-pin connector that goes to the front panel display. Okay, so we'll put that over there, and then we can have a look at this board. I was trying to figure out what was wrong with this board, and I figured it's going to be with the front end power, and so I started tracing out this circuit. So what I ended up doing, and this is a trick I think I quite like now, I started annotating certain planes with voltages that I could figure out were there. And I thought that was a really nice trick for doing this debugging. So you can see I've identified this ground trace here. Now, what I noticed was that we had a power supply in here, and it said 6 volts. And you can see what that connector goes to is this common mode choke. And then I seem to have some inductors and a load of capacitors here. And it looks like the general flow of power is in through this way. But then what I have is these 2 5-volt relays here, with the flyback diodes right outside them. And then down here, what I have is a 5-volt regulator, 5-volt linear regulator. So it looks like what happened, and obviously knowing that this somehow switches between charge and on and so on, it looks like power comes in here, and then these relays do some kind of switching between the voltage source, maybe battery or the charger. And then down here, you actually get your linear regulator, which is actually providing power to the rest of the circuit. So in order to once I traced that roughly out, or got the idea for that roughly out, I thought, well, I could probably just hijack the pins of this, provide 6 volts on its input, and you could see they've written actually on the PCB, input, ground, output. I actually just could attach 2 clips to this 5-volt regulator. If I put in 6 volts, say, into this regulator here, then maybe the whole thing powers up. And sure enough, I did that. And the whole system came back to life. So I know that everything's okay. I've just got an error somewhere with this power circuitry here. So I'm having quite a bit of trouble trying to debug traces here. It's only a simple 2-layer board, but even so, it's hard to see what's happening when we get to these large inductors here. And I don't really want to desolder them unless I have to. So I was trying to think of ways of just trying to see the traces and actually figure out what was connected to what. And what I remembered, I started to try and hold it up against the light, and then what I remembered was I bought for a few pound only, I think these are LED panels for street lights. If I take this PCB and then place it over here, I get a really nice light box effect here, and I can immediately see all the top traces. Anyway, while I was just starting to kind of work through this and realize that this just seems to be some filtering of the power supply, some pretty, careful filtering, I noticed something down here in this little corner. You can just see it on this camera here. It looks like I've popped some kind of 3-pin package down there. So, I mean, first guess is that's a transistor. What I've got here is this burnout transistor. I'm going to try replacing that. And at the same time, try and figure out what's going on with these relays. And I'm assuming that's a transistor. It says Q1. That sounds like some kind of transistor. Okay, a bit of detective work's needed here. So I'm trying to figure out what this burnt out resistor is. So I took a picture using a very cheap microscope, a £10 microscope from Amazon. And obviously has issues with dynamic range. I'm getting a lot of glare here, but it's good enough for me to actually kind of look at this package and try and figure out what it is. There's a few key things to notice. There's, clearly there's a 4 here, so it's definitely ending in a 4. It has this kind of dot in the corner there, and then over here, I think I see a line there, right? I think I see a line there, and that troubles me, because when I saw this 4, I thought, okay, great. I know there's another package on the board with a 4 as well, and that's this package, and this is code Y14, and sure enough, Y14, a PNP device. So I'm pretty sure that what I'm looking at here is a PNP transistor, I would guess, and then I was looking at this other burnt out device, and I'm thinking, you know what? Is that the same? So I spent some time aligning them, and I'm just not convinced now actually about this. Doesn't look like a Y, right? I'm starting to think that this actually looks like, and because the curvature up here, this looks kind of like a B. I looked up transistors in the same package again with this marking B14, and I found an NPN. And it's got about the same current gain. It's in the high gain region for that particular transistor. So I'm looking at these two. I'm kind of thinking that this is actually a B14. So what I then did was I went back to the original package, and I then drew over it with a font that sort of matches what's there. Having aligned the other package underneath this, I'm pretty sure I've aligned the 4. You can see the dots are in slightly different position, but I've aligned the 4 at least. Then what I can do is actually write B instead, and just see if I think that fits. And I don't know, it's this curvature here, right? There's this curve that we have there that really makes me think that this is a B, as well as this kind of straight edge down the side here. What I'm going to do is try and figure out the wiring around the relay, and actually figure out if a NPN or a PNP transistor makes sense. So that's the next step. So we have our relay here, and then this is the supposed blown transistor just down here in blue, and I've got two choices. Either I can say it's an NPN or it's a PNP, and I've put both in, and I'm pretty sure it was a B14, which means it's an NPN transistor. It is the complementary one to this transistor up here, the Y14 transistor that we saw on the board. And that seems to be about right. So if you have a look at this circuit here, if I just kind of put 3 volts into this system, then actually what happens is this lower part of the circuit is not powered up by this upper part of the circuit, so the relay remains open. But then as I put in a slightly higher voltage, we start to get to a point where this thing will switch on. So let's have a look. Not here, not yet. There we are. So we get to 4.8 volts, and that starts to cause this system to switch on. Finally, when we get to 4.9, we have enough to activate the relay, and the relay's open. And it behaves pretty much how you'd expect a circuit that is basically protecting your main circuit from a brownout condition. Yeah. Now, just for good measure, I checked what was happening over here if I actually, instead of putting an NPN transistor in, put a PNP in. And what you notice is you actually get almost no current really flowing through this, 10 milliamps, not enough to kind of trigger this relay model that I've put in. And it doesn't really change, you know. If I up this thing to 6 or 7 volts, I can actually get this to switch on. But then, I don't know, it doesn't seem right that the switch on voltage is as kind of slow as it is. You know, I kind of like the fact that this really does latch one way or the other. This seems to let a small trickle of current through all the time. So I'm pretty sure it's not this, it's not a PNP resistor down here, a PNP transistor down here. And just for fun, one of the things I was checking out was what blows up if you actually reverse bias this thing. And nothing blows up in this case. If anything, I'm just pulling a current down here. So, yeah, this doesn't look like this diode would blow up. A PNP wouldn't blow up. However, if I come to this circuit and try -6 volts, sure enough, this guy blows up. So, yeah, I'm pretty sure that this is an NPN transistor just by analyzing the failure mode. Okay, so let's get that replaced. So I couldn't be bothered waiting for parts to come in to replace this. So I essentially went through my box of transistors that I bought off Amazon, found one with the right gain, and checked its other specs as well. I mean, I'm looking for essentially DC properties here. It's just got a switch on, off and on. And so I just kind of bent the pins into a shape and got it in. So I've had to chisel away the board there. That was actually quite black, and you know, the carbon black can become conductive. So I wanted to make sure I didn't get a short across those at all. Yeah, and I decided to solder this leg direct to this diode here, so that I had actually quite a stiff mechanical joint there to support the diode. And then here I've tried to attach these pads, just because I thought that pad there was probably a bit weakened mechanically from the burn. I used my hot air gun and I've sort of melted the corner of this relay, so I really hope I haven't done any damage there. Yeah, should have perhaps taken the time to put down some Captain tape to protect that while I was using my hot air gun. Yeah, sure enough, the would you believe it, the center pin of the conductor is ground, and the outside is the positive, and you don't see that often. It's not the usual one, but that's why this got reverse biased, because it's not the typical connection. Yeah, center pin ground. So even after the replacement transistor, it didn't work. I was putting 6 volts in here, but pretty much not seeing 5 volts anywhere else in the circuit. So I started to have to trace this out to try and figure out where the 5 volts was going. Now, obviously, the issue was this fuse is blown. I've blown this fuse. Yeah, we can see that this is a 1 amp fuse, but sure enough, it's open, so it needs replacing. So what I'm going to do is instead try putting a little hook probe after the fuse, live dangerously, and I'm going to try putting 5 volts straight into the unit by bypassing that instead. Let's see what happens when we put 5 volts into it. Yay! Oof, that's loud. So while I'm waiting for that to come in, I thought I'd try out an idea. And what I've done is I've put a little Schottky diode here to try and be some kind of reverse polarity protection. But I'm having a little bit of an issue. It's wise to my games. It said it's got an error A4. And if we check out the manual for this piece of equipment, A4 alarm is the voltage is low. So although I put this reverse protection diode in, I'm probably either going to have to try jacking up the input power or just removing that diode, I think, so that the 6 volts can work again. So I think we'll do that and replace the fuse. Actually, this is getting weirder and weirder. If you have a look at the manual, the power is clearly marked as 7 volts. And I've removed the diode and just kind of bridged out this blown fuse for now, because I'm using my power supply, but I can only get this to actually switch on without a warning, right? And now we can actually operate this thing. Yeah, it's actually working. With 7 volts, right? But I'm if you look at this thing, it says 6 volts, right? 6 volts is what it wants. And that says 6 volts as well on the back. But in fact, it needs 7 volts. And I'll be honest, it probably could use more. Or at least certainly this 5-volt regulator would be fine with a higher voltage. So what I think I'm going to do is I'm not going to put this, I'm not going to put that Schottky diode in. I might actually switch back to using my using a proper diode, like a normal diode with a half-volt drop, and then I've only got 6 or 9 volts on this kind of cheap wall wart. I'm wondering if I set this to 9 volts with a half-volt drop across a diode, a reverse protection diode, that might do the trick, right? I'll be running at 8.5 volts, and I think that's fine. I don't think I have any issues with running at 8.5 volts here. So my current draw's gone up a little bit, but nothing I could see in the circuit suggested that was wrong. So yeah, it's ready to go. It's actually giving me, this is atmospheric pressure here, so we're at 1.011 atmospheres. Sorry, that's not quite true. 1013 is an atmosphere, so we're slightly below standard atmospheric pressure. So we're ready to give this a go. The first thing we need to do is load it with Snoop, and this has a little straw to let you do that. So we're going to pop that straw in. Careful not to the first of those blue lines. Great. There's the Snoop. Next, we're going to prepare our gas. So we've got our gas ready to go. And what we're going to do is just turn it on. So I've set a gas flowing through it. I'm just going to hit start. So it's quite hard to show you this, but I think there might be a mechanical failure here. So if I hit start, what you can see is this dips and pulls up a bubble, but the bubble is pinched below the entrance. So if I start to put air into this at a slow flow rate, you can see the bubble doesn't quite go up high enough to go into the flow chamber, even with quite high gas flow rates for this thing, right? That's pretty high. However, if I just kind of, I've opened the back, but if I just kind of drop that pin just a little bit further, all of a sudden that goes through. Really slow flow rate. So it's drying out, it's drying out, it's drying out. It's now over the surface of the gas. It took half a second to transition. I'm trying to let the flow, make the flow slow enough that you can actually see this thing work. But obviously, the more gas you send through, the more it dries that bubble. So you do have to wait for that bubble to dry out enough that it then makes contact. So we're still not, I think it's about to make contact. Still no bubble. Oh, there it is. As soon as I let up the gas a little bit, it flows through. So you see twin on. I just haven't got I need a properly controlled mass flow controller. So we're going to take this into the lab and actually do some tests with it. But I'm willing to declare that as fully functional. I think that works perfectly, exactly as it should. Just out of interest, so you know, the back of this unit looks like this. You can see we've got this kind of mechanical actuation here. If I just hit start, that's how that works. You can see we've got a little stopper thing here that causes it to pause once it gets through a full cycle, and some just some basic logic here. Okay, I'm going to count that as a successful repair. We're going to take this into the lab and see what we can get out of it.